So good afternoon, everybody. So for our seminar today, we have Professor Martin Kunz from the University of Geneva that is going to give us a talk about cosmological applications with Euclid. So thank you, Martin, for giving the seminar today, and you can start now.
Thank you very much, Edwin. Thank you for the invitation. So it's a pleasure, and I'm looking forward to when I'm in person next time visiting Durban and generally South Africa. I'll be talking a bit about Euclid and how we are plan to use it. And it is, of course, now really a pleasure that I can actually show pictures of rockets and things since I think I started working on Euclid in about 2008, and so it's been taking a while to get to this point. So what am I going to talk about? So first I will introduce a bit Euclid and what it does, and some actual data, which is non-cosmological, but nonetheless, just to show you that Euclid is taking pretty pictures. That's roughly the first half. And then in the second half, I'll be talking more specifically about dark energy and modified gravity, and a bit how we can model it, about what we currently know and what we expect to learn from Euclid. And so I think there will be time for questions at the end, but if you have any questions during the talk, you can also ask them directly. So here are some pictures and key numbers of Euclid. So this here is the satellite after it was assembled. And so you can, well, you can't see, but it's about 5 meters high, 4 meters wide, has about 2-ton wet launch mass. It's effectively a telescope. And so this here is the telescope part, this here is the sun shield, and down here are the detectors and the rest of the things needed to have a satellite. So it's not a very big telescope. It has a 1.2 meter primary mirror, which you see here. However, because it is in space, it has an excellent image quality, so it reaches nearly the quality of the Hubble Space Telescope. It is, however, much wider field of view, as we will see. It was launched last year on July the 1st by SpaceX for various political complications that we can discuss afterwards if you want. It sends back about 100 gigabytes of compressed data a day. The nominal mission duration is in principle 6 years. In reality, it's probably going to be about 6.5 years for reasons that we can get to later. And so here, let me show you if it works. And if you can hear it, let me show you briefly the launch because I really love seeing it.
8, 7, 6, 5, 4, 3, 2, 1.
So one thing that I haven't actually, one thing you cannot see here is how bright these flames are. They are much brighter than they look on screen. So that was quite impressive. So you see the launch pad. We were somewhere to the bottom left, far away.
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare
for max Q, she was going to say. But, let's stop it here. So Euclid goes to L2, so it passed. So these are 5 dots spaced by 5 days. So it passed after about 3 days the moon orbit, and then it goes into this very wide orbit. I think the wide orbit is similar to JWST, if I remember, while Gaia has a much tighter orbit somewhere close in. So on the right, you can see a picture taken from the ground by CFHD about 12 days after launch, so when it was here. So it's really actually impressive that you can see Euclid pass by, but it's a fairly big camera. The insertion was extremely good. So basically there was nearly no correction needed. So once it was launched, it just coasted on this trajectory and inserted itself. And that means that actually Euclid has about fuel for about 10 years. And so if nothing else breaks, it's probably possible to significantly extend its mission beyond its nominal life. That though is going to be an ESA decision and not really relevant in the near future. So what does Euclid actually do? So it contains two instruments. One of them is the visible imager, and that one takes very sharp images, and the other one is a near-infrared spectrophotometer. So it does two things. On the one hand, it takes near-infrared images in several color bands, and the other thing is it does spectroscopy, and you'll see some example later. And the idea is that these two together, they do a photometric survey that can be used for V-cleansing and as a photometric galaxy survey. And here we get the spectroscopic galaxy survey, and I will say a bit more later why this combination is particularly useful. So in total, we should get of the order of 1 to 2 billion galaxies for the photometric survey, over actually 14,000 square degrees these days, and about 30 million spectra. All of that's the wide survey, and in addition there will be a deep survey that is mostly for astrophysical results. So Euclid in the end, actually I will not really talk about that. Euclid does cosmology, but it will also be a treasure trove for astrophysics, and potentially its impact in astrophysics may be bigger than in cosmology, even though of course we hope that it will also revolutionize cosmology. And so yes, so why these two things? Why a galaxy clustering and a V-cleansing survey? So what does it measure? So in the galaxy clustering, as you know, since you're all cosmologists, there is this BAO signature, which is this typical correlation size that we can use to measure distances. That's one. And the other thing is for the spectroscopic part is the redshift space distortion. So the fact that if you have some overdensity, galaxies behind fall towards the overdensity, and so they are blue shifted towards us, and galaxies in front fall away from us, and so they are red shifted. And this gives this smearing out effect that we can use to say statistically something about the density distribution in the universe. Okay, and so that's specifically for the redshift space distortions, we need this precise 3D distribution, so the spectroscopic survey. And so that's the 30 million redshift with a high spectroscopic accuracy. And the second part is the photometric survey. So the main application for that is V-cleansing, so cosmic shear, the distortion of objects as we see them through the cosmic web. So here is a bit the symbolic picture, and here is a power spectra about this effect. So here we see the deflection of light, which also is due to the overdensities in the universe. And so this, as I will explain later in a bit more detail, this will allow us to probe two different parts of the metric, and that will be crucial to distinguish different models of dark energy and modified gravity. But of course, we can use this galaxy catalog is not only for the distortion of the galaxies, but we can also use it to have the distribution, and so this is often called 3 times 2 point for V-cleansing, galaxy clustering at the cross, and that will be like 1 to 2 billion galaxies. Okay, so that of course is the theory. How is the practice? Here is a very early commissioning image shortly after Euclid got to L2. And so here you see the actual, an image taken by all its CCDs. So it has 6 by 6 silicon CCDs of about 4K by 4K each. And they observe in one white band in the visible. The choice to use only a single band was to maximize image quality. And so here you see a cutout of one of these CCDs. And if you look closely, you can see here there's some funny streak. This is a cosmic ray. So when you go further away from Earth, like L2, you are outside of the protective magnetic field of the Earth, and you get a lot of these cosmic rays, and that's simply something you have to deal with when you are there. Okay, then there are also some optical ghosts and other things that need to be mitigated. But overall, it has really an amazing image quality with an incredible resolution that's several times better than what you can do from Earth simply because of the atmosphere. It's effectively diffraction limit, and it gets this pixel size. It gets over a field of view that's much bigger than the moon. Actually, I should have included some picture of how big is, I think, the typical JWST is probably not much bigger than my laser pointer size here. So it is, of course, JWST has a much, can collect much more light, and also has a higher resolution, being a much bigger mirror, equally diffraction limited, but it has such a small field of view that it would not be able to do the survey that Euclid plans to do. So Euclid is balancing its image quality and its large field of view to efficiently map the sky. So that's the visible image. And in the near infrared, you see here its focal plane, and so here there are 4x4 near infrared arrays about 2K by 2K, so they have a less high resolution, because here the goal of here is not to measure the precise shape, but to complete the galaxy survey in 3 bands, so that will help with photometric redshifts. And in addition, it can use a grism to do slitless spectroscopy, and then you get these smeared out images, and then you have to cut them out and reconstruct spectra. Okay, so that is what Euclid actually sees. And yeah, so what it saw at first looked more like here on the right. Actually, not only that, so apart from the cosmic rays that I already mentioned, what was realized very quickly was that there was too much background light. And that's, of course, fairly catastrophic if you want to see faint objects. So what was realized was that there is a thruster that peaks out from behind this huge sun shield that's exactly there so that no sunlight comes in, and it's shiny, and so the light scatters off these thrusters, somehow gets through the thermal insulation. I think we still are not sure how it gets through that. Maybe there is a hole. Somehow scatters off one of the mounting legs of the shutter, and then ends up on the visible focal plane, which is not further shielded inside. Okay, so some of my ESA colleagues were kind of banging their heads against the wall when that was realized, because they actually knew that thruster was looking out from behind the sun shield, and they had been worried about the thermal impact. So they had modeled how heat gets conducted into the satellite, but they had never expected that it could scatter light into the satellite. But so effectively, since this thruster is here, so what can be done is you can turn the satellite a bit until this nozzle disappears behind the sun shield seen from the sun, and that solves the problem. But it puts extra constraints on the survey design. It makes it more complicated to find a good sequence of observations, and that's why the survey is probably going to take 6.5 years and not 6 years to be seen. The other thing that was realized when it was there was that we launched right into a solar activity maximum, and so the sun at the moment is very active, and it sends out X-ray flares. And so we periodically, I didn't put the picture here, but they're quite funny. We periodically get X-rays of the sun shield that on our CCDs, and that just has to be mitigated by removing these bits. That's not really a big problem. What was the main worry was that in the beginning, Euclid was taking these kind of images, and what happened here was that the fine guidance sensor was confused by the X-rays and tried to focus on the X-rays, and then it lost the lock on the sky stars. And so here you see the stars going going all over the focal plane as the satellite goes like whoops. Okay, and that was a big worry, but luckily it could be solved with a software patch after a couple of months. So this would have been the end of the mission had it not been possible to solve this with software. Okay, so all of these problems were solved. And then the latest news was that another problem appeared that was expected to appear. And that's the fact that the satellite is put together on Earth. And so automatically there is like Earth air inside, and the air on Earth contains water. And this water gets absorbed to some extent in the multi-layer insulation. And then when it's in space, it outgasses, and then it freezes onto the coldest objects as ice. And this ice, even at the few nanometers, at the few molecules depth, starts to absorb a significant amount of light. And so that was then observed that the throughput started to decrease. And it is possible to evaporate that ice. You can just basically turn the satellite towards the sun. The drawback is that this heats the satellite to such an extent that you probably have to recalibrate it, and Euclid needs an extremely precise calibration that takes weeks. And so that would be fairly disruptive. And so for that reason, there are heaters integrated, and so the engineers just tried to guess where the ice was, and so they turned on the heater for that element, which was a folding mirror number 3. And so you can see here the light throughput, or how much it changes, and you can see that as soon as this mirror reached the ice sublimation temperature, then the throughput started to increase as the ice on it became gaseous. And so you can see that this actually all happens at very low temperature in vacuum. And so at this point, the expected throughput was restored again. So at the moment, everything looks fine. Okay. So what's the timeline looking like? So here was the launch year was somewhere to the left. So on this picture, it's here. Here was the start of the nominal mission that I tried to align. We are now somewhere here. So we are within the nominal survey, okay? And so the way this is supposed to work, so we are still within the early survey operations, but after about 1 year, there should be a quick look, a review, plus the internal delivery of the first year of data, and then we have 1 year to write papers. And then after about 2 years, there will be the first data release, and then there will be a quick look, and then will be the second data release, and then 2 quick looks, and then the final data release. So you can expect that you get, in about 1 year, you get smaller survey areas, more for astrophysical purposes, and in about 2 years, there should be the first cosmology results if everything goes well. Fingers crossed. Okay, but the very first thing we did with Euclid, that was a request by ESA, was to take some pretty pictures. These are called the early release objects, and that was to highlight Euclid capabilities, particularly for the ESA Director General at the ministerial conference last autumn. And so the pictures I'm going to show you, there were supposed to be more, but because of the fine guidance issues, in the end it was limited to these 5 objects, and the time for these 5 objects was about 1 day of observation of Euclid. And so each of these objects is a single 0.7 square degree observing block. That's the field of view that you saw. So each of them is about 1/30,000th of a Euclid survey. And so it contains effectively about 600 megapixel of visible data, 45 megapixel of the near-infrared data, and the spectra. The spectra haven't been released yet. And so this should give you maybe some idea of how big this Euclid survey will be. And so I'm just going to show you just these 3 so that you can see some pretty pictures. So the first one is the Perseus cluster at about 74 megaparsec. The cluster itself has about 1,000 galaxies, but there are estimated about 50,000 galaxies in the image. And then a closer irregular galaxy that is also a Cepheid host. So there are Hubble observations that can be cross-compared. And then the Horsehead Nebula, just because it's so beautiful. Let me actually comment on that when we get there. So this is the Perseus cluster. And so the point is that Euclid can take this whole image, the majority of the cluster, in a single pointing, so it doesn't need to put several pointings together. And so I hope you enjoy looking at these pictures as much as I do. And then you can zoom in. So for example, here we can zoom in onto this galaxy, okay? And this is a full resolution picture, I think. So you see how it's much bigger, and you can also see all of those galaxies. I hope the Zoom connection is good enough. So you can see all of those background galaxies. So this galaxy is part of the Perseus cluster, but all of these little ones are the ones that we're really interested in to map with Euclid. And so here is the irregular galaxy. And so here, again, you can take the complete irregular galaxy in a single pointing, and we can zoom in somewhere. And here you can actually resolve most of the stars while still having the complete irregular galaxy as on a single image. And so here you see some supernova remnants. And if you look closely, it's maybe a bit difficult over the zoom. You can see again all of these background galaxies that are Euclid's real target. And then one of my favorite images of the early images, of course, that's a very famous image, the Horsehead Nebula. And so if you're an amateur astronomer, this gives you another idea of the size of the focal plane of Euclid. So usually you don't see these colors because the blue is actually H alpha. So normally the blue is red. And what is red here is infrared emission from dust. So normally this would be black because it's not indivisible, but because Euclid has infrared capabilities, it has both. Okay, and so also here we can, for example, zoom in here to show you the actual resolution that Euclid has. And here again, you can actually see that it's full of galaxies. There is the famous line from 2001, I think it's full of stars, so it's actually full of galaxies. Okay, so that was roughly my first part about Euclid and where we are. So you see that Euclid is actually taking pictures, except of course if I'm cheating and I'm showing you others, but I promise these are Euclid images. And so now let's go a bit to the science. And here is a table that lists the Euclid primary science objective. So in some sense, that's what we promised ESA we would deliver. And so you see that there are 4 main topics. There is dark energy, tests of gravity, which mostly apart from test of cosmological principle, I will call dark energy and modified gravity. Then dark matter, where actually neutrinos are particularly interesting, the neutrino mass, and initial conditions, so basically inflationary parameters, early universe. But today I'm going to talk about dark energy modified gravity, which on the one hand is equation of state, measurement, in particular testing for a dynamical dark energy, giving specific, like a specific precision with which we promise to ESA to do that, as well as measurement of the growth of structure to check whether the growth of structure is consistent with the expansion history, or whether something funny is happening, which we would typically then interpret as modified gravity. But I'm actually going to explain this in a bit more detail. So the way I think about how we model dark energy is that on the one hand, we have the actual observations which observe these pictures and which we turn into catalogs. And on the other hand are the models that we consider as kind of fundamental, which are typically action-based. Okay, so these models, they describe actual physics, but we can also use phenomenological parameters that I will introduce that sit in between and that kind of model the observations or maybe the deviations of the observations from expectations, and that can be mapped basically all the way up to these models. So by looking at those parameters, we will learn where we should be looking there, because we cannot effectively test all of those models. So to explain this in a bit more detail, so that's something that all of you in principle know. So here is your typical astronomer or satellite that looks at something, and typically that something, the light from the something goes through something else, okay? And we try to use these observations to measure the geometry, okay? And the geometry, the metric, determines the left-hand side of the Einstein field equation. And if we know the left-hand side of the Einstein field equation, we also know the right-hand side, and the right-hand side is the stress-energy tensor. And if we know the stress-energy tensor, we can go and look inside, and that will tell us what is in the universe. Is it dark energy? Is it something else? And more explicitly, if we now look at a background Friedmann, Lemaitre, Robertson, Walker type universe, then the observation that we do here are distances. So either luminosity distance for supernovae, but actually for Euclid, it's more the BAO distance where we have a known scale, and we observe the angle under which we see that known scale on the sky. These distances, they're an integral over the expansion rate, and then so basically, if we measure the distances, we can constrain the expansion rate. The Friedmann equation links the expansion rate with the energy density, and here then we can, for example, use the conservation equation where we parameterize the pressure with a W, okay? And so basically, if we measure the distance in several redshift bins, we can measure the expansion rate in several redshift bins. That allows us also to measure the energy density in several redshift bins. And that allows us to constrain this equation of state parameter, which tells us what the dark energy is. Okay, there is quite a lot of small print, of course, that I jumped over. But that's the principle, okay? And now, particularly for the next generation of surveys, we want to do that also at the perturbation level. So at the perturbation level, we can parameterize the metric perturbations with two gravitational potentials. One that's, if you want, is like the time dilation potential, and one that's the curvature, okay? And then if you look, for example, at the geodesic equation or the perturbation equation, the light deflection probes the sum of the two potentials, and the acceleration of non-relativistic objects is the gradient of only one of the two potentials. And so therefore, if we can measure weak lensing or cosmic shear, we can probe the sum of the two. And if we have a precise galaxy catalog with redshift space distortions, then we measure only one of them. And so then we can actually distinguish them, and we can look what they are. And so often we introduce two parameters, mu and sigma, that tell us how the Poisson, the relativistic Poisson equation is modified. So, for example, if there is something more that clusters, then this will show up as a change in mu. Or if there is some change in the way light is deflected, then this will show up as a change in this sigma parameter. And then, in addition, you can also, so there are only two of them, but sometimes we prefer to look at whether the two potentials are the same or not, and then we introduce an eta parameter. But the eta, sigma, mu are linked through this equation, so they are not independent. Okay, and so in the following, I'm now going to show you a bit, well, first I will explain a bit what we expect to see for a typical modified gravity model, and then I'm going a bit to explain what we currently know and what we expect to learn. And so here is a specific model, an F of R model, where the Einstein-Hilbert action, which is just R, is replaced by some arbitrary function of R. And so here, and in basically all of these models, you can consider, basically, you can consider the change as an extra scalar degree of freedom. So you have an extra scalar field. And so the extra scalar field has a typical scale. Here we see it as a mass scale. And so that gives you a typical distance scale as well. And so now you have a scale dependence in your model. So if you look at lambda CDM, in lambda CDM, there is no scale dependence. So the clustering changes, of course, with redshift. So there's more clustering today, but it does not depend on the scale. But in these F of R models, and generically in all of these models, there is now a scale dependence, and so the clustering depends on scale. And so that's one of the fingerprints of such model. And the second thing that you also see here, that while on large scales, the two potentials phi and psi are the same, on small scales, they are not. And so now you have a difference between the two potentials, and this is a fingerprint typically for modified gravity models. And then in addition, on very small scales, you need to hide all of this because this is totally ruled out by observations in the solar system. And so you need also a screening mechanism. And that means that the whole behavior on nonlinear scales becomes quite complicated. And that is one of the technical problems trying to deal with all of these models. Okay, but these two are the two main signatures, so scale-dependent growth and non-vanishing slip, which are kind of the things we are going to look for. So I will actually skip over this slide, and I will assume that you know very well about cosmological observations, so I can just discuss them a bit without going into details, except of course, since I think many of us are probably in HIRAX, so I should say one of the things we are also kind of really interested in at some point is to combine Euclid with HIRAX and do cross correlations. Okay, so what do we know currently about dark energy? So here are there is a recent paper from the Dark Energy Survey that shows an effective quintessence model that has a certain equation of state that is here modeled in the CPL parametrization. So effective quintessence models, they have a scalar field with a high sound speed that doesn't cluster inside the cosmic horizon. And the two potentials are the same, which is here given by the sigma being 0. So the two potentials being same means eta equal 1, and mu on scales inside the horizon is also 1. Okay, and so effectively they're simply given by this W, and so here you can see the constraints is that W0 is somewhere between minus 1.1 and 0.9, minus 0.9, and W0 is roughly 0, but with fairly large error bars. And here is a paper from Planck in which I was involved, where we tested in a binned way to see if there is any evolution of the dark energy equation of state, or if it is -1. And so at this point, there is no deviation of -1. Now, very recently, there have actually been some new results from from DESI, which is a spectroscopic instrument. And here, as maybe you are aware, okay, if you look just at the constant equation of state, you get a very precise measurement, again, around -1. But if you allow for a time evolution, you're actually displaced from W0 -1 and WA0, which is the lambda CDM limit. And so here there is a certain deviation. But the deviation is not extremely strong. And so I personally think we can discuss that maybe at the end if you want. But at the moment, I think it's a bit too early to draw strong conclusions. So we need more data. And what I think is really great is that the DESI, which is a ground-based multiplex spectrograph, so with many fibers pointing at the sky that go to spectrographs, and Euclid, which is space-based and has this GRISM approach where just everything gets smeared out. They're very different. And so I think if this is real, then the comparison between DESI and Euclid will really be able to convince us that there is something real there. Or if it's not, then the two of them should be possible to understand that between the two of them. Okay, so that's roughly what we know about the background equation of state at this time. And so here is what we expect Euclid to do. So this figure of merit that I mentioned already briefly earlier is the kind of the inverse of the error ellipse on W0 WA. So basically how big or how small this error ellipse is. Okay, and we promised to get to about 400, and here you see different data combinations for Euclid. Okay, and you see that in the pessimistic case, pessimistic here means that we don't understand the nonlinear clustering very well. We're actually struggling to get to 400. And if we can use nonlinear scales, then we can get a lot higher. So you see that actually it will be really important. So it's not only about the observations, but it's also about the theory. And so the theory has to be sufficiently good so that we can analyze the model down to small scales, and then we will get very strong results from Euclid, but more or less from any of the current generation of surveys. And if we cannot do that, then then we're a bit in trouble. So it's not only the observers, it's also the theorists who have to deliver. And so here you have some typical errors. And so you can see that the errors here, they're like an order of magnitude smaller on both W0 and WA. Okay. And then in addition, there are other data sets. So here I always only look at the galaxy clustering and the V-cleansing. Okay. And so that was the background, the W, which we can call maybe dark energy, a bit simplified. And then we can look at the perturbations, which we can call modified gravity. So what do we know currently about the perturbations? So here, 0 here means consistent with lambda CDM expectations. So you can see that the redshift space distortions, they measure the mu, because the mu parameter is associated to the psi gravitational potential, which accelerates galaxies that fall into overdensities. So the redshift space distortions measure that. And the V-cleansing mostly measure the sigma. And so together they are nicely complementary and allowed to measure mu and sigma together. And here is another slightly more recent figure from dark energy survey, where you see that it's actually a very similar. The all data contours are actually very similar between the two. Here is a figure from Planck, just because I was in Planck. Here I don't show mu sigma, I show mu eta, because at that time we used that. And so you can see also here that it's consistent. And so this direction is the mu direction, which is less well constrained, and this is the sigma direction. And so you can see that we have about the 5% error on the gravitational lensing parameter, and about 25% on the extra clustering, I would call that the mu parameter. Okay, and so let's see what we expect to reach with Euclid. So this is a fairly busy table. Also, this is not an official Euclid forecast. We're still working on this specific forecast. But you can see that in the optimistic case, we hope to get about percent level errors. So the first thing you also see here, by the way, is that the galaxy clustering mostly measures mu, but not the sigma, while the V-cleansing mostly measures the sigma, but not so much the mu. And so again, you need the combination to be able to measure both. And so you see that we expect to get a few percent level constraints on both parameters, depending also here on how well we can use the nonlinear scales. Okay, and so just very briefly, before I move towards the conclusions, is how well do we do for specific benchmark models like the F of R models that I showed earlier. So here is a slide from the Planck analysis where, okay, so this is some specific F of R model with the parameter B0. B0 is 0 in lambda CDM, and you would probably expect it to be order unity, okay, in this specific model, but you can see that already current constraints are at the level of about 10 to the minus 4, okay? Especially redshift space distortions really push you down. And so the current constraints on this parameter is of the order 10 to the minus 4. And here is a Euclid forecast where the benchmark model is at 5 times 10 to the minus 6. And so galaxy clustering and V-cleansing alone, they struggle to actually be able to detect that model. But when you combine galaxy clustering and V-cleansing, then it's like 10 sigma detected. So meaning that we expect to have constraints of the order of 10 to the minus 6 with Euclid on the equivalent parameter. So again, more than an order of magnitude better than what we currently have. Okay, so let me then slowly summarize. So to get, so as I mentioned in the beginning, Euclid is successfully launched. It's there, it's operating nominally. There were some challenges, but luckily we were able to overcome all of them, and now it's in the main survey. Euclid and other surveys, so there is DESI, there will also be LSST, and later Roman. they will significantly tighten dark energy and modify gravity constraints. Of course, also others, but today I focused a bit on that. But of course, what we really would like to see is a deviation from a cosmological constant. So in this sense, the recent DESI results are really exciting because they give us a clear target that we can focus on. But there are challenges not only on the observational side. So we not only need more and better data, but we also need to be able to analyze it with the required accuracy, and that's a challenge for theorists and simulators for the nonlinear scales. And I should say, you see, that actually goes beyond just understanding the model, but on small enough scales, there is also baryons that get in the way. And I find it really ironic that we try to understand these mysterious things like dark energy and dark matter that we don't know anything about, but one of the ingredients that we have the most problems with are baryons that we think we kind of understand, but because of their highly nonlinear physics, shocks, and so on, that's actually very difficult to model in these simulations. So then, as I said, not only Euclid itself, but also Euclid combined with other data will be great. So for example, Euclid cross-correlated with HIRAX. Okay. And so to give you an idea, so there will actually be the science papers out for these early release observations that I showed you the pretty pictures towards the end of May. Then in about March next year, there will be the quick look release, where there will be some mostly astrophysical results. And roughly in the summer of 2026, we expect the first cosmological results from Euclid. Okay, and so I think it's about 40 minutes, and so I'll stop at this point. And if you have questions, thank you.
Okay, thanks again, Martin, for the very interesting presentation. So we can start with the questions. If anybody has questions. Yes, Bruce.
Hi there. Thanks, Martin. That was great. Obviously, one of the interesting possibilities with the DESI results is that there's late time evolution. I'm not sure. How would you characterize Euclid's sensitivity as a function of redshift relative to DESI, putting you on the spot? Do you have a sense of, if there is, for example, an equation of state that's actually increasing towards, are you likely to have more sensitivity than DESI for late time evolution or less?
That's not totally easy to answer. It's actually, so at some level, DESI and Euclid are actually also quite complementary, because DESI is the DESI, like the main galaxy part, is actually a lower redshift than Euclid. And so Euclid starts, so I should say Euclid has two. It has the photometric one. That one is very different from DESI, which is spectroscopic. That there is a good redshift overlap. So there it's possible to actually compare the two. So in terms of BAO, that should be stronger at some point than DESI, because Euclid will be 14,000 square degrees. And that goes to low redshifts. The spectroscopic survey will be higher redshift. So for the W, I would expect Euclid to be better at some point. But for example, for redshift-based distortions, there, which is not out yet, so we don't know what those will show, there DESI will probe the lower redshifts and Euclid the higher redshifts.
Awesome, thanks. Maybe while I've got you, can I ask, let's say that W is increasing, right? Is there a model that you would go, oh yeah, that would be my go-to favored model to explain that? So it's more of a theory parameter space question.
Not at this point. I mean, the thing is, if you look at the DESI results, now we talk about DESI. If you look at the average curve, actually, let me see if I can jump back to that one. Let's see how easy. That was not a good idea to do that. Because the weird thing, or I don't know, the new cosmic coincidence, it just insists in being this way around. The new cosmic coincidence is a bit that if you just have a constant W, you are actually exactly at -1. And then in the evolving one, your W naught is less negative than -1, and your WA is more negative. So if let's see, if this is today, instead of a cosmological constant, you kind of tilt your W around kind of the middle of the redshift range of DESI. And and so that means you cross the phantom divide, you cross W equals -1. You start in the phantom regime and you cross it upwards and you end up at like -0.8 today in W. And that I find a bit weird. I don't know. I mean, normal scalar fields simply don't do that. You have to already go to the slightly more involved models, either, I don't know, modified gravity or kinetic gravity braiding or something. And so then the clustering data should, for these kind of models, the clustering data may give you additional hints if it's really that. So it will be really interesting to see what happens for the non-BAOs. So the redshift space distortion specifically for DESI.
Absolutely. I mean, could you not have been like -1 and now it's evolving to like minus towards 0, for example?
That's an excellent question, and that would have been for that you need to have you need to actually look at the data. So I haven't actually had time, but I'm sure there probably are already papers out looking at that. Because right, they looked only at constant and this linear relation. And so to answer that question, you need to have you need to give more freedom to your W.
You might almost want to, like some sort of 4-parameter model for W.
Yeah, let me
I wonder what that could be.
There is, let me just quickly drag another plot over from the DESI page. Now, of course, we do a DESI talk, and I'm not in DESI, so I cannot speak for the collaboration. But this is I think this is one of their plots, if I actually manage to center it on my screen. Okay. And so it would have been great if they actually had redshift here, but you can guess the redshifts from these plots. So you can see that actually looking at, but I guess this is actually from their CPL parametrization, so it doesn't tell us so much really. So I think it has to be phantom in order to go down, and then it has to be then it has to go up in order to come back. So somehow in this redshift range, you have to be below the lambda CDM curve for your distances. So whatever gives you that.
Cool, thanks, Martin.
Okay, any more questions from? No. Okay, I have a question. So okay, sorry, there is a question from Tony. Go ahead, Tony.
Hi, thanks, Martin. That's very interesting talk. I was just going to ask in the beginning, you alluded to some politics around the choice of rocket that you used. Can you maybe say a few more words about that?
Yeah, that was global politics, because originally Euclid was supposed to be launched on a Soyuz, and that became then unavailable like a bit more than 2 years ago.
Right, the Russian
yeah, the Russian invasion.
Russian rockets, right? I see.
Exactly.
Okay,
It was a Russian rocket. So the rocket was already, so it was supposed to be launched from French Guiana, from the ESA spaceport, but ESA used quite a lot of those rockets. And so the rockets are there. The ESA bought them already, but the Russian crew left. And so then they couldn't be launched on those. Then we were supposed to launch them on Ariane 4. Right here, which one is? I always get a bit confused. Ariane 5 is the current one, but all the Ariane 5 launches were already booked. Okay, so the nominal rocket then was Ariane 6, which was the backup launcher. But Ariane 6 still hasn't had its maiden launch, so it became relatively quickly clear that there would be there would be significant delays. And in addition, Amazon put in a big order for Ariane 6 launches because they probably didn't want to give the money to Elon Musk, since he's a competitor. And so we were really worried, and ESA as well were really worried that that those might go actually in front of Euclid. And then we might have been pushed behind Roman, and since Roman is somewhat similar to Euclid, that would have been a bit of a disaster. And so then ESA actually, the ESA Science Directorate checked what are the alternatives and did early tests whether SpaceX, whether Falcon 9 would work. And they saw that it would work, and then we had to kind of convince our governments that they would support it. And because our governments, they get money back if it's an Ariane launch, but of course, if the money goes to the US, then it's gone in some sense. And so I know that France was not happy at all, because France is probably the majority shareholder of Arianespace. Switzerland was also not happy, but in the end, they agreed not to block it. And so ESA was allowed to talk, they were allowed. So I think we realized in about 2 years ago that there was a problem. In the autumn, in the late autumn, the ministers allowed ESA to talk with SpaceX. And I think by kind of January or so, they had a contract with SpaceX. And then the launch slot that was available was half a year later. And it's also really amazing because usually Ariane has, or ESA has like launches every month or two, and SpaceX has launches weekly, basically, and so it's a totally different operation. So that was also, I think, quite impressive and quite different for our ESA collaborators, because they had to adjust quite a bit. And actually, I don't know, do you have time to chat a bit more about this? There was also a funny thing. So when we were at the launch, we were supposed to go the evening before and to see Euclid standing ready for launch, and the SpaceX staff kept delaying, but they didn't say a word why. They just pretended there was no hurry to go there. And then eventually we went there because it was not possible to delay it further, and Euclid was still horizontal, because in SpaceX it actually gets put together horizontal and then put upright before the launch. And so it turned out, they never told us, we only heard that from our ESA people, that there was a nitrogen leak on the platform, and for that reason they couldn't put Euclid on the platform. And in ESA, that would probably have taken weeks to fix, because they would have had to first find out where is the leak, then like a strategy review how to fix the leak, then get someone in to fix the leak, then tests whether the leak is fixed, then another review whether everything is fine, and then they could have decided on a new launch slot. And so basically at 1 a.m. when our mission manager came in to prepare the launch, they brought in everyone they could think of, and then in about 3 hours, I think, they found the leak, they fixed the leak, they made sure it was okay, and they put Euclid upright. And the next day at 11, Euclid was launched. So that was really impressive. So we actually didn't see. So the picture in the beginning, that's a SpaceX picture, because we couldn't go so close anymore the next day when it was all ready. So we saw it from much further away. But it was a fairly exciting launch as well.
Oh, thanks. Interesting. Yeah, sounds stressful. Thanks, Mark.
Okay, more questions. We have time for one more question. Okay, so my question was about the public data release. So is going to take in stages, or is going to how is you mentioned that into your presentation at some point, but I didn't saw the yes, so it's going to take by stages.
Yes. So basically the DR1 is the data after 1 year. That's about 2,500 square degrees. That's going to be maybe a bit more that's currently available. Okay, then there is basically the data at this point. Then we have 1 year to analyze it and write the data. Okay, write the papers. Then the DR2 is is the 1, 2, 3-year data. So that's about 7,500 square degrees and 1 year to analyze it. So see, that's going to be 4 years after launch, right? DR1 is going to be about 3 years after launch, but 2 years after a bit more than 2 years after survey operations start. So in 2 years, okay? Then that will be in 4 years, and that will be 7,500 square degrees. And then DR3 is then the full 6 years of survey. So that is then going to be the 14,000 square degrees. But that one is still going to take a while.
Okay, thanks.
And in between, there are these quick releases which are there to get the community from falling asleep, which are smaller, but probably deeper data which are more useful for astrophysical analysis. So what we call legacy, even though, as I said, that may well it may well be that this will be the real legacy of Euclid. But I mean, it's a bit like in Planck. So in Planck, there were also 3 data releases, and they were also spaced out quite a bit. So, but yes, it's still going to take a while until we will be releasing the first cosmology data. Even though we have, I mean, right now, this is not really official, so I don't have it on the slides. But I think we are soon going to reach 1,000 square degrees actually observed, and like 100 million galaxies or so. But basically, the internal data release will only be in about a year, and then it's another year to actually make it public, at least.
Okay, thanks. Okay, so I think there is no more questions. Okay, so we can say again thanks to Martin for the talk today, and to everybody for coming. And yes, I will send emails about in the following weeks for our next seminars. So thanks, Martin, again. So see you in the next seminar. Thanks, everybody.
Thank you very much for the invitation. See you
You're
again.
welcome. Bye.
Bye.